gets all the parameters correctly, and depending of which type of property it is, it's going to have a different invoke function. For example, if it's going to be a string, there is invoke functions called put string or put variant, etc., or depending how many arguments it has a completely different invoke functions. The invoke function basically just transform all the elements in order to actually call the function that is in charge of this setter or the getter or the method. And the actual function that is going to do all the setter and getter is the resulting from the objects from UUID and the function index. The function index is basically an index to the vtable that allow you to get into the function. Now, all that works just to get string allocation. So that's how Explorer are these days, hard. So basically, you end up in this function, which is, as you can see, a function that is allocating from the process heap, which is the default heap, and it's allocating the size that you're sending. And then after that, it's doing a mem copy for the new allocated memory, just like it is. It's not copying like the the length at the beginning of the object. So that's helped us to exploit this bug. And that's how we did it. But there are actually easier ways by doing dynamic analysis, which is basically what we actually did too. We create a small immunity debugger script, which we are going to release at some point, which basically do very simple stuff. First of all, it set a hook on getThisID that allows me to obtain the number of the name of the property and the ID of that property once obviously the function is being called. And then whenever invoke x gets triggered, which is the actual function that is going to call our method or our property, we set up at the beginning of that function, we set up the allocation and the allocation hooks. The RTL allocate heap hook was going to give us the size of whatever is allocated during that method of property. And then we have RTL free heap, which is actually the one that's going to free that memory. And finally, at the end of invoke x, because basically we are a breakpoint at the beginning of invoke x, setting the hooks with all the allocations, and then we are setting a hook at the end. So whenever that gets triggered, we set all the allocation and the allocations at the end of invoke x. We unset all those hooks, and then we have like a nice list of things that happen during that invokes, which is what we're looking for. And basically, in order to test it, we just create a small script that basically loops over all the properties on an object and just put as random string. And that's what basically we found. Like just by basically or randomly passing the properties with a string, you get, as you can see here, this is the actual property that's being called, hidden. And then you can see that this property is actually allocating two memories, 1 and 2. One of them is being free. And then basically we have at the end of invoke x a small script that tells you if a memory leak was found or not. It's not a real memory leak, but it's still something that during the life of that invoke x or that call to the property of method was allocated and not deallocated. And so basically we can see that this allocation here of a size of 18, which is based on our string, it was actually allocating a string, and as you can see, the first few words are our control. This is in Unicode, but you can easily change it into ASCII. And so we did it with all the different properties, and we know now how we can potentially, do an allocation of the exact size that we want. So now that we have all the elements, the exploitation is very, very simple. You have first, we free the object, an object that we now understand what it is, and that we can decrease at the moment we want. That's the first moment. Then we allocate the chunk through the DOM properties. This is how use after fish should be being done nowadays. And I know there are people doing that. It's not like rocket science, but just a way to show how it works. And then finally, you use the object, which is now under your control. You control the vtable, you can use it. Now, hit tray now makes sense. Like you can now hit tray and point it into a place where you know that the hit tray will actually gonna be there, not just randomly pointing to something that you know, you might control or not. So the second fact of the day is winners use heap spray consciously. I mean, it's not bad to use heap spray, but you have to use it understanding what's going on. So this is like a bonus slide, basically on Internet Explorer 8. They fixed the common heap spray, and basically if you do that, I think Skyline was the first guy that made that heap spray. If you do that, it won't work. So basically when we start doing Internet Explorer 8 exploits, we start like thinking, oh, well, how we can allocate and do a heap spray by doing like circular memory leaks and all kind of complex stuff, and then in the end it was very simple. We were just, instead of using directly a string, we were using a reference to the first entry of an array, and works perfectly. So that's what we are using. And there are many ways to do it. I hope they don't fix that, but if they fix, there are other ways. So how do you do it in a non-traditional way? How do you exploit use after free in a non-traditional way? And basically what we came out with is object replacement, but I didn't see it on the wild, but probably might be some people doing it. Basically, instead of just replacing it with a string, we're going to replace it with a different object of the same size, but with a different vtable. It's not easy, but it's possible. And this would allow us to be more precise, because we are not just jumping into a random heap spray. We are actually using another vtable for different stuff. And the interesting part is that either we'll be able to get direct execution, or we will be able to change the primitive. And that's a good thing. And I guess what is more important about this technique is that you can change the primitive into an info leak. And nowadays, like every exploit needs an info leak. I mean, even this client side, an info leak is the big part of an exploit. Especially if you want to do it APT, if you don't want to fill that guy memory with like 500 megabytes of memory of a heap spray. So you have to be precise. So in order to get also the info leak will allow you not only to obtain information on the heap, but also will allow you to obtain DLLs and then do the return to libc or ROP, etc. So info leaks are now a big part of every exploit, especially if it's a new Windows versions. So in order to exploit use after free by replacing an object, the first thing you want to do is to identify the triggering function. Now, the triggering function, I mean, of the original object. So you are freeing an object, which in our case we were doing an element. Now I need to know which things are the actually, methods are the actually ones that will allow me to actually trigger my modified vtable. And once you identify all the different methods that you are allowed to, in my case, I was doing through JavaScript, so I have to try to find out the many ways I can do from JavaScript in order for the same object to get different functions, because then we're going to replace it from something else. So we need to find out not only the different ways to exploit it, but also the different type of arguments and the amount of arguments that I am actually receiving on the original functions. So in the case we were doing TROF, and TROF have like get this ID and for example addref, release, those things I was able to trigger it. So that gives me what is called, or we call it, a trigger offset. A trigger offset, which means that it's an offset from the beginning of the vtable to the function. So once I know the trigger offsets, so this is for example an example. Now in my this is a version of our of a trigger of the same bug, the appear bug, and basically it's called an ECX plus 1C. 1C is actually get this ID. So now I know that from a JavaScript I'm allowed to call get this ID, and I know that 1C will be my triggering offset. They will be important. And as many offsets I can find, the more functions I could be able to later replace. So basically, these are the finds that I found by trying to replace. Obviously, addref, which means going to increment the counter. if I just set to a property, this is an element dot whatever, and I set my object to that, it's actually going to increase the reference. Then by doing delete the objects, I'm going to actually release the object, so that will call the offset +8. Get this ID by just calling whatever or trying to get any property or actual method. It's going to call get this ID. Then I have delete member name, just by trying to delete whatever. It doesn't matter if it exists or not, because that's usually resolved in runtime. So by doing delete p dot some property name, I'm going to actually call the offset 24. And then finally, this the get net this ID, which is basically the way you usually loop over all the properties. And that actually got the offset 34. And once we got all the offsets, we need to know if we have those objects, we have something that we control. Can we control the arguments that we are sending to that function? And this is, and the other important thing is how many arguments that function has. For example, in the case of get this ID, as you guys remember, what you send is a string of the name of the property you're looking for. If it doesn't exist, it doesn't matter, because basically it's trying to resolve that. So if it doesn't exist, we will return as a this property doesn't exist. But it do it through get this ID. So basically one of the arguments will be our control, because it's a string. In our case, create element as a string. And in the case of delete member name, exactly the same. The name you can see here, blee, is basically a string. So you can send another string, something you control, and then you have one of the arguments of that method our control, with a string or whatever. So once you know exactly all your triggering offsets, now you know for each triggering offset, you know how many parameters you are sending to that function, and then you know which ones are in your control, etc., etc. Now you have to find all the potential objects that you can replace with that original object. And that could be very, very hard to find. It is. But it's possible. There are, in fact, a lot of objects of that size. And that's why at the beginning I said that if you can control what you are freeing, it's better. Because in our case, we were stuck to 28 bytes, which was the tier of interface. But if you can, potentially you can send different stuff, then you have different sizes of those objects to play with. And then you can find way more replacement objects to exploit. So once you find all the list of different objects, and you can see here, right, if you do it with IDA, it's very simple. It's just search immediate value, because usually objects are allocated with a fixed value because they're always the same size. So you will see like a push something, then call new or call malloc, whatever. And then at the end, you will see that it's actually creating all the objects. So if you, with IDA, you just search immediate value, you get the list of all the immediate values, and then you just order it by instruction, and you just go to push, and that's pretty simple, and then you find all the push 28. So once you find all the different objects, you need to check the vtable. The first thing that you want to avoid is every object that looks exactly like yours. Like if my object is actually doing get this ID, I'm screwed, because get this ID will work as it's supposed to work, and then it doesn't make much sense to me. Basically, I'm replacing an element with another element, and I mean, I couldn't get anything out of that. But there are other types of objects that has the same different methods at the same triggering offsets. And once you find all of that, you need to check all the triggering offsets you have. That's why if you have more triggering offsets, it's better for you. And you have to find out all the arguments of that method and how they use it. Because if you know that, you start combining things and you see like, oh, this argument is the string to get this ID. But in this case, it's being used in order to save some pointers. That's win. That's basically an inflict. So, or it's using that string as an object, and it's actually calling the vtable directly from that string. That's another win.